At the heart of nearly every galaxy, hidden in the swirling darkness, lies a monster so powerful it bends the very fabric of reality around it. We're talking about supermassive black holes, cosmic titans with masses millions or even billions of times greater than our Sun. These aren't just voids in space, they're active, hungry forces that shape the destiny of entire galaxies. Imagine something so dense that not even light can escape its grip, warping spacetime like a stone sinking into a cosmic pond. And yet, despite their terrifying nature, these black holes hold secrets that could rewrite our understanding of the universe itself. What if I told you that a supermassive black hole doesn't just sit there silently? It feeds, it flares, and it even sings rippling spacetime with gravitational waves that echo across billions of light years. Some of these giants were born in the early universe, growing faster than science thought possible, while others lurk quietly, their presence betrayed only by the frantic orbits of stars caught in their invisible grasp. How did they get so big? What role do they play in the birth and death of galaxies? And perhaps the most chilling question of all, what happens if you get too close? Today, we're diving deep into 30 astonishing secrets of these galactic beasts, uncovering how they form, how they behave, and why they're far more than just cosmic vacuum cleaners. From the way they can fling stars across the universe like slingshots to the mysterious jets of energy they blast into space at nearly the speed of light, every revelation will leave you in awe. This isn't just a tour of the universe's most extreme phenomena, it's a journey to the edge of what we know and beyond. By the end, you'll see the night sky differently, knowing that every galaxy's heart holds a secret, and that secret is a supermassive black hole. So let's begin, because the universe isn't just stranger than we imagine, it's stranger than we can imagine. Every galaxy that sprawls across the night sky, from the grand spirals to the glowing ellipticals, has a silent ruler at its center, a supermassive black hole. These aren't just ordinary black holes, they're the titans of the cosmos, with masses so immense they dwarf entire solar systems. Picture something with the weight of millions, even billions of suns crushed into a single point, warping space and time so severely that nothing, not even light, can break free once it crosses the event horizon. That's why we call them supermassive. They don't just exist, they dominate, shaping the very galaxies that host them. Take the Milky Way, for example. At the heart of our own galaxy lies Sagittarius A, a supermassive black hole with a mass 4 million times that of our Sun. Yet, even that pales in comparison to the true giants out there, like the one lurking in the galaxy M87. In 2019, humanity witnessed a milestone, the first ever direct image of a black hole's shadow, revealing the glowing ring of superheated gas swirling around M87's monstrous core. That glowing halo, captured by the Event Horizon Telescope, wasn't just a scientific triumph, it was proof that these enigmatic beasts, long theorized but never seen so clearly, are as real as the stars above us. But here's the fascinating part: supermassive black holes aren't all the same. Some, like Sagittarius A, are relatively quiet, while others are voracious eaters, tearing apart stars and blasting out jets of energy so powerful they can be seen across the universe. Their sizes vary wildly too, from the small ones with a few million solar masses to the true leviathans, tipping the scales at tens of billions. How did they grow so large? Some might have formed from the collapse of massive early galaxies, while others could have merged, swallowing smaller black holes in a cosmic feeding frenzy that spans billions of years. One thing is certain: these monsters in the middle aren't passive. They're dynamic, violent, and essential to the story of their galaxies. Without them, the universe as we know it wouldn't exist. They're the architects of chaos and order, the invisible hands guiding the birth and death of stars. And as we peel back their secrets, we're not just learning about black holes, we're uncovering the hidden rules of the cosmos itself. The growth of a supermassive black hole isn't just a slow crawl. It's a cosmic feeding frenzy on a scale that defies imagination. These monsters start small, perhaps as the remnants of massive early stars, but over billions of years, they balloon into giants through a combination of gluttony, violence, and sheer defiance of physics. One of the most straightforward ways they grow: relentless eating. Picture a black hole sitting at the center of a galaxy, surrounded by swirling clouds of gas and unfortunate stars that wander too close. As this material spirals inward, it forms an accretion disk, a glowing, superheated whirlpool of matter. The black hole devours it all, growing heavier with every bite. But sometimes they don't just nibble, they gorge. In a phenomenon called super-Eddington accretion, a black hole consumes material so fast that it temporarily breaks the theoretical limits of how quickly it should be able to feed. Normally, the intense radiation from an accretion disk should push material away, like a cosmic wind blowing against the inflow. But under extreme conditions, gravity wins. The black hole forces matter down its throat faster than physics textbooks say it should, packing on mass at a staggering rate. Some scientists think this might explain how supermassive black holes grew so big so early in the universe's history, reaching billions of solar masses when the cosmos was still in its infancy. Then there's the brutal dance of mergers. When galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational embrace. They circle closer and closer until bang, they merge, creating an even larger black hole. These cosmic smash-ups release titanic bursts of gravitational waves, ripples in spacetime that we've only recently learned to detect. Imagine two giants becoming one, their combined mass shaking the fabric of the universe itself. But there's another shadowy player in this growth: dark matter. While invisible and elusive, dark matter's gravitational pull may funnel extra gas and stars toward the galactic center, indirectly feeding the black hole. Some theories even suggest dark matter could interact with black holes in ways we don't fully understand, perhaps accelerating their growth beyond what visible matter alone can explain. The result: a behemoth that didn't just grow, it conquered. Whether by feasting, merging, or bending the rules of physics, supermassive black holes rise to dominance through methods as varied as they are extreme. And with every discovery, we're piecing together how these titans came to rule the hearts of galaxies. One of the greatest cosmic mysteries isn't just how supermassive black holes grew so massive, it's how they existed at all when the universe was barely out of its cradle. Astronomers have spotted these behemoths shining as quasars less than 700 million years after the Big Bang, a blink in cosmic time. How did they get so big so fast? The answer lies in their origins, and scientists are locked in a heated debate between two competing theories, each more mind-bending than the last. The first idea suggests these giants grew from smaller seeds. In the early universe, massive stars, hundreds of times heavier than our Sun, burned bright and died young. When these stars collapsed, they could have left behind black holes with masses of maybe a few hundred suns. Over time, through relentless feeding and mergers, these seeds ballooned into the supermassive monsters we see today. But here's the problem: even with constant feasting, the math struggles to explain how they packed on billions of solar masses in such a short time. The universe was still a toddler when these beasts were already fully grown, so something doesn't add up. That's where the second, more radical theory comes in: direct collapse. Instead of starting small, imagine vast clouds of primordial gas, pure hydrogen and helium from the dawn of time, collapsing in one catastrophic plunge. No star formation, no intermediate steps, just a straight freefall into a black hole with tens or even hundreds of thousands of solar masses right from birth. These black hole seeds would have had a massive head start, gulping down gas and merging with others to reach supermassive scales while the cosmos was still in its infancy. It's like being born a sumo wrestler instead of working your way up from lightweight. Yet even this theory has its wrinkles. For direct collapse to work, the gas clouds couldn't fragment into stars first. They had to stay smooth and cool, a rare scenario in the turbulent early universe. Some simulations suggest this might have been possible in regions bathed in intense ultraviolet light, which prevented the gas from splitting apart. But proof remains elusive, buried in the faint whispers of light from the universe's first billion years. What's truly baffling is that both theories might be right. The early cosmos was a wild, diverse place, and supermassive black holes could have formed in multiple ways, some sprouting from star-sized seeds, others born as giants from the get-go. The James Webb Space Telescope, peering deeper into the past than ever before, is now hunting for these primordial black holes in their infancy. Every new discovery chips away at the mystery, bringing us closer to understanding how these cosmic titans came to rule the universe before it even had a chance to grow up. Crossing the event horizon of a black hole isn't like hitting a wall. It's more like stepping over an invisible threshold where the universe's rules switch off one by one. This boundary, the point of no return, isn't a physical surface but a gravitational trap where escape becomes impossible, even for light. Picture a river flowing toward a waterfall. Once you pass the edge, there's no swimming back. That's the event horizon, a silent, invisible line where gravity's grip becomes absolute. But not all event horizons are created equal. Take the classic Schwarzschild black hole, the simplest kind. A perfect sphere of darkness where gravity is so intense that space-time warps into a one-way street. Nothing fancy, no frills, just an inescapable pit. Now introduce spin and everything changes. Kerr black holes, named after physicist Roy Kerr, rotate so fast they drag space-time around with them like a cosmic whirlpool. This spin flattens the event horizon into an oblate shape, creating a swirling zone called the ergosphere just outside it. Here, space-time itself is pulled along, as if the black hole is twisting the fabric of the universe into a vortex. The difference is staggering. While a Schwarzschild black hole is a static sinkhole, a Kerr black hole is a dynamic, churning maelstrom. Matter caught in the ergosphere can't just fall in. It's whipped into orbit, flung around at relativistic speeds. Some particles even get slingshotted outward, stealing energy from the black hole's spin in a process so wild it sounds like science fiction. And then there's the singularity. In a Schwarzschild black hole, it's a single, infinitesimal point where all the mass is crushed, a place where physics as we know it breaks down entirely. But in a spinning Kerr black hole, the singularity becomes a ring, a loop of infinite density where gravity and centrifugal force balance in a nightmare of contradictions. Some theories suggest passing through this ring might not destroy you. It could spit you out into another universe or time. Of course, no one knows for sure, because once you cross the event horizon, there's no way to send back a postcard. What makes the event horizon truly bizarre is that it's not just a barrier, it's a cosmic illusion. To an outside observer, an object falling toward a black hole appears to slow down, frozen in time as light stretches into infinite redshift. But for the doomed traveler, time flows normally as they plunge into oblivion, a paradox that shows just how warped reality becomes near these monsters. The event horizon isn't just a boundary, it's a hall of mirrors where space, time, and physics unravel in ways we're still struggling to comprehend. If you ever find yourself plunging toward a black hole, here's a grim piece of advice: don't look down. The forces at work near the event horizon don't just kill you, they turn death into a grotesque physics experiment called spaghettification. Picture this as you fall feet first toward the black hole. Gravity's pull on your toes is exponentially stronger than on your head. The difference isn't a gentle tug, it's a violent stretch, elongating your body like cosmic taffy until you're ripped apart atom by atom. Even sturdier fare like stars don't stand a chance. Take Assassin 14 Li, a star that wandered too close to a supermassive black hole. Astronomers watched in horror as tidal forces, the same stretching power that gives Earth its ocean tides, but amplified by a factor of billions, peeled the star apart like an overripe fruit. Over weeks, the black hole's gravity shredded the star into a glowing stream of plasma, swirling into the accretion disk in a final, brilliant scream of X-rays and radio waves. This isn't just destruction, it's physics at its most extreme. Tidal forces near a black hole are so intense because gravity's strength isn't uniform. A few thousand miles closer to the singularity, and the pull becomes exponentially fiercer. For smaller black holes, spaghettification happens well outside the event horizon, meaning you'll be torn apart before you even cross the point of no return. But with supermassive black holes, the event horizon is so vast that the gradient of gravity is slightly gentler. You might actually cross it intact, only to face an even more surreal fate. Inside, tidal forces would still stretch you, but now space itself is flowing inward faster than light, carrying you toward the singularity like a leaf caught in a cosmic hurricane. The remains of Assassin 14 didn't just vanish. They became a beacon, a flickering flare of energy that helped scientists measure the black hole's spin and mass with unprecedented precision. Every star torn apart this way is a gruesome but invaluable lab for studying how black holes feed. Some even spit out debris at nearly light speed, as if the black hole is playing with its food before swallowing. Underneath the horror lies a profound truth. Spaghettification isn't just about annihilation. It's about transformation. Matter stretched into streams becomes part of the black hole's accretion disk, fueling jets of energy that can outshine entire galaxies. In a twist of cosmic irony, the same forces that destroy also create, turning stars into the building blocks of a black hole's violent legacy. The universe doesn't waste anything, not even tragedy. The glow of an accretion disk isn't just light, it's the scream of matter being torn apart at the atomic level. Picture a swirling maelstrom of gas, dust, and stellar debris spiraling toward a black hole at nearly the speed of light. As these particles collide and churn, they don't just heat up, they become a cosmic furnace, radiating energy so intense it can outshine every star in the galaxy combined. This isn't your average campfire warmth. Temperatures in these disks soar to millions of degrees, transforming the material into a seething plasma that blasts out X-rays and ultraviolet light across the universe. What fuels this brilliance? Two ruthless forces, friction and magnetism. As matter orbits the black hole, particles rub against each other violently, like sandpaper grinding at relativistic speeds. This friction doesn't just warm the disk, it supercharges it, converting kinetic energy into heat with terrifying efficiency. But the real twist comes from magnetic fields, which twist and snap like rubber bands in the chaos. These fields channel plasma into jets and funnel energy outward, accelerating particles until they emit high-energy radiation. It's like a natural particle accelerator cranked up to cosmic extremes. The result, a light show unmatched in the universe. Quasars, the cores of distant galaxies powered by supermassive black holes, are so luminous they drown out their host galaxies entirely. Some shine with the brightness of 1 trillion suns, visible billions of light years away, and it all traces back to the accretion disk where ordinary matter becomes extraordinary energy. Even in our own Milky Way, when Sagittarius occasionally snacks on a passing gas cloud, its disk flickers to life, offering astronomers a front-row seat to this dazzling physics in action. But here's the paradox. The disk's glow isn't just a byproduct of destruction, it's a cosmic recycling program. The energy released regulates how fast the black hole feeds, pushing material away even as gravity pulls it in. This delicate balance determines whether a black hole feasts quietly or erupts as a quasar, shaping the destiny of its entire galaxy. The accretion disk isn't just a spectacle, it's the engine of the cosmos, turning annihilation into illumination on a scale that defies belief. Some supermassive black holes don't just consume, they spit. With terrifying precision, these cosmic monsters can launch jets of plasma so fast they approach the speed of light, stretching thousands of light years across space. These aren't gentle streams but focused beams of raw energy powered by the black hole's rotation and magnetic fields. Think of them as the universe's ultimate particle cannons, capable of punching through entire galaxies. At the heart of this phenomenon is the black hole's accretion disk. As matter swirls toward oblivion, not all of it crosses the event horizon. Some gets caught in the black hole's twisted magnetic fields, which act like cosmic railguns, accelerating particles along the poles. The result, twin jets erupting in opposite directions, composed of electrons and protons hurtling at nearly 99% light speed. These jets glow fiercely in radio waves, X-rays, and gamma rays, marking their paths across the cosmos. The most extreme examples come from active galactic nuclei, or AN, where supermassive black holes feast voraciously. The jet from galaxy M87, for instance, stretches 5,000 light-years visible even to amateur telescopes. But it's not just about size. These jets transform their surroundings. When they slam into intergalactic gas, they carve out colossal bubbles, heating the material and preventing it from cooling into new stars. In galaxy clusters like Perseus, jets from the central black hole have sculpted cavities so vast they could swallow our entire Milky Way. Here's the twist: these jets aren't just destructive. By stirring up galaxy clusters, they regulate star formation, effectively putting a cap on how large galaxies can grow. Without them, the universe might be overrun with even more stars, altering the cosmic landscape entirely. They're a paradox born from chaos, yet imposing order on scales we're only beginning to understand. What's truly astonishing is how long these jets persist. Some flicker, but others remain stable for millions of years, their energy output dwarfing anything humanity could ever produce. They're testament to the sheer power locked within a black hole's spin, a reminder that even in the darkest corners of space, the universe refuses to be quiet. Quasars don't just shine, they blaze with the fury of 1,000 galaxies, outshining every star in their host galaxies combined. These cosmic beacons, the brightest persistent objects in the universe, are powered by supermassive black holes in a feeding frenzy. But they're not just random flares of light, they're precision instruments. Their brilliance revealing secrets about the cosmos that would otherwise stay hidden. At their core, a quasar is the visible echo of a black hole's insatiable hunger. When gas, dust, and stars fall toward the event horizon, they don't vanish quietly. Instead, the material forms an accretion disk so energetic it glows brighter than anything else in the universe. The friction and magnetic fields in this disk heat the matter to unimaginable temperatures, converting mass into radiation with terrifying efficiency. Some quasars emit more light in a single second than our Sun will over its entire 10 billion-year lifespan. What makes quasars truly special is their role as cosmic lighthouses. Because they're so luminous, we can spot them even at the edge of the observable universe. The light from the most distant quasars has traveled for over 13 billion years, carrying with it a snapshot of the cosmos when it was less than 1 billion years old. By studying the way this light interacts with gas and dust along its journey, astronomers can map the large-scale structure of the universe. Quasars act like backlights, illuminating the cosmic web of matter that would otherwise remain invisible. But quasars aren't just relics of the past, they're also time machines. The spectrum of a quasar's light contains absorption lines, tiny gaps where intervening gas clouds have absorbed specific wavelengths. These lines form a unique fingerprint, revealing the composition and temperature of the gas between us and the quasar. Some of these clouds are as ancient as the universe itself, preserving the pristine conditions of the early cosmos before stars polluted space with heavier elements. There's another twist: quasars are fleeting. They shine only as long as their black holes have abundant fuel. Once the surrounding gas is exhausted, the quasar dims, leaving behind a quieter supermassive black hole like the one at the center of our own galaxy. This means the quasars we see today are cosmic fossils, their light a delayed message from an era when black holes ruled the universe more visibly than they do now. The most distant quasars also challenge our understanding of black hole formation. How did supermassive black holes grow so massive so quickly after the Big Bang? Their existence hints at unknown processes in the early universe, perhaps involving exotic physics or ultra-efficient feeding mechanisms. Every new quasar discovered pushes the boundaries of what we thought possible, forcing us to rethink the rules of cosmic evolution. Quasars prove that black holes aren't just destroyers, they're creators of light, structure, and knowledge. Without them, the universe would be far darker and our understanding of it far dimmer. They're not just powerhouses, they're storytellers whispering secrets across billions of years. Not every supermassive black hole is a ravenous beast. Some sit in eerie silence, barely making a ripple in the cosmic pond. Take Sagittarius A, the 4 million solar mass giant at the Milky Way's heart. Unlike its flashy quasar cousins, it emits barely a whisper of radiation, dormant for millennia. But this quiet isn't permanent, it's just waiting. The difference between active and dormant black holes comes down to one simple factor: fuel. Without a steady diet of gas, dust, or stars, even the mightiest black hole becomes a sleeping giant, its accretion disk fading to a faint ember. Why do some go quiet? Imagine a city's power grid. When electricity flows, lights blaze, but cut the supply and darkness settles. For black holes, the power grid is the surrounding galaxy. In gas-rich environments like young galaxies or colliding systems, material constantly funnels toward the center, feeding the beast. But in older, calmer galaxies like ours, most nearby gas has already been consumed or blown away by stellar winds. Sagittarius A isn't lazy, it's stranded in a cosmic food desert, with only the occasional scrap drifting close enough to nibble. Then comes the wake-up call, a tidal disruption event. When a star strays too close, the black hole's gravity stretches it into a stream of plasma, igniting a sudden feast. In 2019, astronomers witnessed this firsthand when a normally quiet black hole in a galaxy 215 million light-years away flared to life, shredding a sun-like star. For months, the glow from that stellar debris outshone the galaxy itself, proving even the quietest monsters can roar back to life. These events are rare, happening maybe once every 10,000 years per galaxy, but they're cosmic alarms signaling a black hole's dormant power. The silence of Sagittarius A might feel unsettling, but it's a gift. An active black hole at our galactic center could bathe the Milky Way in deadly radiation, sterilizing planets across thousands of light years. Dormancy isn't weakness, it's a balancing act, a reminder that even the universe's most violent forces have cycles. And when the next star falls, we'll be watching, ready to decode the secrets whispered in its dying light. It starts with a paradox, a force of destruction that somehow creates. Supermassive black holes don't just sit at the center of galaxies, they shape them, controlling the birth and death of stars with invisible gravitational hands. This isn't just coincidence, it's a cosmic feedback loop, a delicate balance where the galaxy feeds the black hole, and the black hole, in turn, dictates the galaxy's future. Take star formation, for example. Without black holes, galaxies might churn out stars unchecked, exhausting their gas reserves in a frenzy of stellar births. But supermassive black holes act like cosmic thermostats. When they feed, their jets and winds blast outward, heating surrounding gas to millions of degrees, too hot to collapse into new stars. It's as if the black hole is saying, enough. The evidence is etched across the universe. In galaxy clusters like Perseus, X-ray observations reveal vast cavities carved by black hole jets, regions where star formation has been snuffed out entirely. Meanwhile, in starburst galaxies where stars form at dizzying rates, black holes often lie dormant, their feedback silenced. The correlation is undeniable. Active black holes suppress star birth, while quiet ones allow galaxies to blaze with youthful stellar activity. But there's a twist. These same winds that stifle star formation also recycle. By pushing gas outward, they seed the galaxy with enriched material, heavy elements forged in stellar explosions, fueling future generations of stars and planets. It's a self-regulating cycle. The black hole gorges, erupts, and then settles, its outburst setting the rhythm for galactic evolution. The most stunning proof comes from quasars in the early universe. Their fierce radiation and winds likely prevented nearby gas from forming stars too quickly, allowing galaxies to grow steadily rather than burn out young. Without this regulation, today's universe might lack the stable spiral galaxies where life could arise. So the next time you gaze at the Milky Way's calm splendor, remember, its beauty isn't accidental. The quiet giant at its center, Sagittarius A, may seem dormant now, but its past eruptions helped craft the galaxy we call home. Black holes aren't just inhabitants of galaxies, they're their architects, sculptors, and silent guardians. For decades, the Hubble Space Telescope has been our window into the violent, brilliant lives of supermassive black holes. But nothing prepared astronomers for what it would reveal about their origins. Staring deep into the cosmic past, Hubble spotted quasars blazing when the universe was less than 1 billion years old, their black holes already weighing in at billions of solar masses. These weren't just anomalies, they were cosmic impossibilities, challenging everything we thought we knew about how quickly black holes could grow. If they formed from the collapse of early stars, they'd need to eat faster than physics seemed to allow, swallowing gas at rates that should have torn their accretion disks apart. The discovery sent theorists back to their chalkboards, scrambling to explain how nature built giants in what felt like overnight. Then came the James Webb Space Telescope, and the mystery only deepened. JWST infrared eyes pierced through dust clouds Hubble couldn't penetrate, uncovering black holes in places no one expected, like tiny, primordial galaxies barely large enough to host them. One standout is galaxy Sears 1019, a speck of stars smaller than the Milky Way yet housing a black hole over 10 million times the Sun's mass. According to conventional wisdom, galaxies and their central black holes grow in lockstep, but JWST found rebels breaking all the rules. Some dwarf galaxies hosted black holes 100 times heavier than predicted, as if the tail was wagging the cosmic dog. The most shocking revelation: these early black holes might not have needed stars to form at all. JWST detected traces of direct collapse black holes, primordial behemoths born from collapsing gas clouds without a stellar middleman. Their fingerprints are in the light of distant quasars, whose spectra show oddly pristine surroundings, lacking the heavy element stars produce. It's as if these black holes appeared fully formed, like cosmic Athena springing from the void. Hubble and JWST didn't just add pieces to the puzzle, they shattered the old picture entirely. Every new observation suggests black holes didn't grow in predictable ways, but through chaotic, hyper-efficient processes we're only beginning to grasp. The universe, it seems, had a cheat code for building giants, and we're just now deciphering it. When black holes collide, the universe itself shudders. On September 14, 2015, humanity's most sensitive ears LIGO, the Laser Interferometer Gravitational Wave Observatory, caught a whisper from across the cosmos. For the first time, we detected gravitational waves, ripples in spacetime caused by two stellar mass black holes spiraling into each other 1.3 billion light-years away. The signal lasted just 0.2 of a second, but in that fleeting moment, science changed forever. The merging black holes, 29 and 36 times the Sun's mass, converted 3 suns worth of matter into pure energy, vibrating spacetime like a drumhead. LIGO and its European counterpart, Virgo, work like cosmic microphones. Their L-shaped arms, each 4 kilometers long, fire lasers down vacuum tubes. When a gravitational wave passes, it subtly stretches one arm while squeezing the other, shifting the laser's interference pattern by less than 1,000th the width of a proton. Detecting this requires near superhuman precision. Earth's ambient noise, from earthquakes to passing trucks, constantly threatens to drown out the signal. Yet against all odds, these observatories have now captured dozens of mergers, painting a violent picture of a universe teeming with colliding black holes. But what about the giants? Supermassive black hole mergers would unleash waves 1,000,000 times stronger, with frequencies so low they'd take years to pass. Current detectors can't hear them, their arms are too short. That's where future missions like LISA, the Laser Interferometer Space Antenna, come in. Slated for the 2030s, LISA will consist of 3 spacecraft forming a triangular detector with arms 2.5 million kilometers long, floating in perfect harmony. These won't just catch mergers, they'll track the black hole's dance for decades as they spiral closer, culminating in a crescendo that shakes the fabric of reality. The implications are staggering. A supermassive merger might warp spacetime enough to briefly distort the light from every star in the sky. The energy released could outshine all the stars in the observable universe combined for months. And hidden in those waves would be answers: how often galaxies merge, how black holes grow, even how spacetime itself behaves under extreme strain. But here's the tantalizing part: some of these collisions might have already happened. Light from distant galaxies takes billions of years to reach us, meaning we're seeing them as they were in the past. Their black holes could have merged eons ago, and the waves from those events might already be washing over Earth undetected for now. When LISA launches, it won't just listen to the universe, it'll open a portal to the past, revealing the ghostly echoes of collisions that shaped the cosmos. Stephen Hawking's greatest puzzle wasn't about what black holes devour, it was about what they erase. According to classical physics, everything swallowed by a black hole is lost forever, crushed into oblivion at the singularity. But quantum mechanics insists that information can never truly disappear. It can only be scrambled, like a cosmic game of hide and seek. This contradiction, known as the information paradox, has haunted physicists for decades, threatening to unravel our understanding of reality itself. Imagine tossing a book into a fire. The pages burn, but in principle, every word could be reconstructed from the smoke and ashes. The information still exists, just transformed. Now throw that book into a black hole. Hawking's calculations suggested the information would be permanently erased, as if the universe's ledger had pages ripped out. The problem: quantum laws forbid this. Particles entering a black hole must leave some trace of their existence, even if only in the subtle correlations between Hawking radiation particles escaping the event horizon. Otherwise, the past becomes unknowable and physics loses its predictive power. For years, the paradox seemed insurmountable, but recent breakthroughs have cracked open a possible solution: entanglement islands. Picture the event horizon not as a sharp boundary, but as a fuzzy surface where quantum entanglement, a spooky connection between particles, creates hidden pockets of information storage. These islands, theorized to exist just inside the black hole, could act as cosmic backup drives, preserving data even as the black hole evaporates. The information isn't destroyed, it's encoded in the radiation in ways we're only beginning to decipher. The implications are staggering. If correct, this means black holes aren't the ultimate shredders we once thought. They're more like cryptographic puzzles, scrambling information so thoroughly that it takes cutting-edge physics to decode the message. Experiments with holographic principles and quantum simulators are now testing these ideas, offering glimpses into how spacetime itself might store data at the most fundamental level. Hawking himself ultimately conceded that information probably escapes, but how it happens remains one of the most thrilling open questions in physics. The paradox isn't just about black holes, it's a battle for the soul of reality. forcing us to choose between the deterministic cosmos of Einstein and the probabilistic world of quantum theory. And somewhere in that tension, the truth is waiting. Black holes aren't eternal prisons, they're cosmic ice cubes, slowly melting away over timescales so vast they dwarf the age of the universe itself. This evaporation, known as Hawking radiation, is one of the most mind-bending predictions in modern physics. It all starts with quantum mechanics, where empty space isn't truly empty. Instead, it's a seething sea of virtual particles, pairs of matter and antimatter that flicker in and out of existence too quickly to be detected. Normally, these particles annihilate each other instantly, leaving no trace. But near a black hole's event horizon, something extraordinary happens. If a particle pair appears right on the edge, one might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. To the outside universe, it looks like the black hole just emitted radiation, a faint whisper of particles carrying away its mass. The smaller the black hole, the faster this happens. A stellar mass black hole might take 10 to the power of 67 years to evaporate, but a supermassive one, you'd need to add another 50 zeros to that number. To put it in perspective, the largest known black holes would take longer to vanish than the current age of the universe multiplied by a trillion. Here's where it gets stranger. As a black hole shrinks, it doesn't just fade quietly, it goes out with a bang. The final moments of evaporation unleash a burst of energy equivalent to millions of hydrogen bombs, a final defiant flash before disappearing forever. Of course, no one will ever witness this. By the time the last supermassive black holes begin their final decay, the universe will likely be a cold, empty void, all stars long dead and galaxies dissolved into darkness. Yet the existence of Hawking radiation solves one paradox while creating another. If black holes can vanish, what happens to all the information they swallowed? Quantum mechanics insists information can't be destroyed, but Hawking's original calculations suggested it might be. This conflict, the infamous information paradox, remains one of physics' greatest unsolved puzzles. Some theories propose the information is encoded in the radiation itself, scrambled beyond recognition but technically preserved. Others argue it's stored in remnants so tiny they defy detection. For now, Hawking radiation remains theoretical. No telescope has ever detected it directly, but its implications are undeniable. Even the universe's most indestructible monsters have an expiration date. They might outlive stars, galaxies, and even time as we know it, but nothing lasts forever, not even a black hole. What if black holes aren't just cosmic dead ends but secret tunnels through spacetime? The math of general relativity allows for this tantalizing possibility. Structures called Einstein-Rosen bridges, better known as wormholes. Picture a black hole's singularity not as a crushing oblivion but as a gateway, a shortcut connecting two distant points in the universe or even different times. The equations suggest that under very specific conditions, the extreme warping of spacetime near a black hole could, in theory, stitch itself to another region, creating a bridge. It's the ultimate cosmic cheat code, a way to cross thousands of light years in a single step. But before you pack your bags for a wormhole vacation, there's a catch. These bridges are catastrophically unstable. The moment anything tries to pass through, even a single photon, the tunnel would snap shut like a rubber band stretched too far. The reason: gravity. In a traversable wormhole, you'd need some form of negative energy or exotic matter to prop the throat open, counteracting the natural tendency of spacetime to collapse. And here's the problem: no one's ever found proof such materials exist. The closest we've come is the bizarre world of quantum mechanics, where virtual particles exhibit negative energy for fleeting instants, far too weak and brief to stabilize a wormhole big enough for a human, let alone a spaceship. Even if you could stabilize one, the journey would be unpleasant. The tidal forces near the entrance would likely spaghettify anything attempting passage long before it reached the theoretical tunnel. And then there's the time travel paradox. Wormholes that connect not just space but different moments in time could create causality loops, scenarios where an effect precedes its cause, violating the bedrock rules of physics. Imagine a scenario where you travel back and prevent your own birth. The universe tends to frown on such contradictions, which is why many physicists suspect nature outright forbids traversable wormholes. Yet the idea persists in cutting-edge theories. Some models of string theory and quantum gravity suggest wormholes might be entangled on a fundamental level, linking black holes across vast distances like quantum teleportation on a cosmic scale. Others propose that wormholes could be holographic projections, with their true endpoints existing in higher dimensions. These aren't just sci-fi musings, they're active areas of research, pushing the boundaries of what we consider possible. For now, wormholes remain locked in the realm of speculation, their existence hanging on the delicate balance of unproven physics. They're a reminder that even in the darkest corners of space, the universe keeps its most bewildering secrets just out of reach. The holographic principle turns our perception of reality inside out. What if everything we see, from swirling galaxies to supermassive black holes, is just a projection from a hidden two-dimensional surface? This mind-bending idea springs from string theory and the ASTRONOMY correspondence, a mathematical framework suggesting that the universe might work like a cosmic hologram. Picture a black hole's event horizon not as a simple boundary, but as a shimmering screen encoding all the information about what's inside. The three-dimensional space we experience could be an illusion, a rich tapestry woven from data stored on a distant, flat surface. At the heart of this theory lies a paradox: black holes seem to destroy information, yet quantum mechanics insists it must be preserved. The holographic principle offers a solution. The information swallowed by a black hole isn't lost. Instead, it's smeared across the event horizon like ink on a stretched canvas, forever imprinted in two dimensions. This isn't just abstract math. Physicists like Juan Maldacena have shown how a black hole's interior, a volume of space, can be perfectly described by equations operating on its bounding surface. It's as if the universe has a built-in compression algorithm, storing 3D complexity on a 2D hard drive. The AD/CFT correspondence, a specific realization of this idea, links two seemingly unrelated theories: gravity warping spacetime inside a hypothetical anti-de Sitter universe AD/S, and a quantum field theory without gravity operating on its boundaries CFT. Though our universe isn't exactly anti-de Sitter, the correspondence hints at a profound truth that gravity and quantum mechanics might be two sides of the same coin. Black holes become the ultimate test case, their event horizons acting as translators between dimensions. If the holographic principle holds, it rewrites our understanding of space itself. The vast emptiness between stars, the depth of a black hole's interior, all of it could be a carefully crafted illusion, a shadow play cast by interactions happening on a distant, flat edge. This doesn't just solve black hole paradoxes, it suggests the universe is far stranger, far more interconnected than we ever imagined. Reality might not be what we see, but what we can't see, encoded in a hidden layer just beyond perception. That glowing ring in the famous first image of a black hole isn't just an artist's impression, it's the edge of reality itself. When the Event Horizon Telescope unveiled the shadow of M87's supermassive black hole in 2019, it showed us something no simulation could match: a dark void encircled by a fiery halo of light, warped into a perfect ring by gravity's immense grip. This wasn't just a pretty picture. That halo, called the photon ring, is a cosmic funhouse mirror, bending starlight into a loop so extreme it reveals the black hole's deepest secrets. The darkness at the ring's center isn't the event horizon. It's something far stranger. Light from behind the black hole should be blocked entirely, but gravity curves spacetime so severely that photons skimming just outside the horizon get whipped around in a final orbit before escaping to our telescopes. This creates the illusion of a shadow roughly 2.5 times wider than the actual event horizon, a silhouette framed by trapped starlight. The sharper the ring's edge, the more precise our measurements of the black hole's mass. And the brighter one side glows, that's the Doppler effect in action, betraying the direction of the black hole's spin as it drags spacetime around it like cosmic molasses. But the real magic lies in the photon ring's substructure, a series of nested light rings like tree rings marking time. Each layer represents light that looped around the black hole once, twice, or dozens of times before breaking free. The tighter these rings, the stronger gravity's grip, offering a direct test of Einstein's general relativity under conditions no Earth lab could ever replicate. When scientists analyzed M87's shadow, they found its shape matches Einstein's predictions to within 10%, a triumph for a theory formulated over a century ago. Future observations aim to capture even sharper images, perhaps revealing the black hole's fingerprint, subtle flickers in the ring caused by magnetic fields or clumps of infalling gas. Some theorists even suggest we might one day spot the elusive photon sphere, a region where light orbits the black hole indefinitely, creating ghostly echoes of the universe's past. Every detail in that shadow is a message carved by gravity waiting to be decoded, and with each new observation, we're not just seeing a black hole, we're reading the universe's own handwriting. Imagine a black hole so vast it could swallow our entire solar system like a speck of dust, and still have room for thousands more. That's TON 618, the universe's most massive black hole ever discovered, weighing in at a staggering 66 billion times the mass of our Sun. To put that in perspective, if you replaced our Sun with this cosmic titan, its event horizon would stretch well beyond Pluto's orbit, engulfing planets, asteroids, and even the Oort cloud in its infinite darkness. The scale is almost incomprehensible, a single object with more gravitational pull than some small galaxies. But how does something like TON 618 even form? Most supermassive black holes grow over billions of years, feasting on gas, dust, and the occasional star. Yet TON 618 existed when the universe was barely a toddler, its immense size defying conventional models of black hole growth. One theory suggests it started as a direct collapse black hole, a primordial monster born from the collapse of an enormous gas cloud in the early cosmos, skipping the star stage entirely. Another possibility is that it gorged itself during an era of extreme galaxy mergers, swallowing smaller black holes and entire star clusters in a feeding frenzy that lasted eons. What's truly baffling is its appetite. TON 618 isn't just massive, it's active, shining as a quasar, so bright it outshines the Milky Way by a factor of 100. The energy it releases, powered by its insatiable accretion disk, could sterilize entire swaths of the cosmos around it. And yet, despite its fury, it's eerily distant, over 10 billion light-years away, a relic from a time when the universe was young and chaotic. Studying TON 618 isn't just about setting size records. It's a window into the extreme physics of the early universe, a place where the rules we know might not apply. Could there be even larger black holes lurking in the cosmic shadows? For now, this behemoth holds the crown, but the universe always has a way of surprising us. For decades, astronomers have been tracking black holes of two distinct classes: stellar mass black holes formed from collapsing stars, and supermassive behemoths anchoring galaxies. But between these extremes lies a cosmic mystery: the missing middleweights, black holes with masses between 100 and 100,000 suns. These intermediate mass black holes, or IMB, should exist in theory, bridging the gap in our understanding of how supermassive black holes grew so large so quickly. Yet spotting them has been like searching for invisible elephants in a cosmic labyrinth. the hunt has led scientists to some of the universe's most unexpected corners. Take the globular cluster Omega Centauri, a dense swarm of millions of stars orbiting the Milky Way. Here, stars whip around an unseen gravitational anchor at dizzying speeds, something massive enough to hurt them but far smaller than a supermassive black hole. Similar clues have surfaced in dwarf galaxies like Henry's 210, where X-ray flares and erratic star motions hint at a hidden predator of intermediate size. Even more compelling is HLX-1, an ultraluminous X-ray source 12 million light-years away, flaring with the energy signature of a black hole roughly 20,000 solar masses, too big to be stellar, too small to be supermassive. So why are they so elusive? Part of the problem is their stealthy nature. Unlike supermassive black holes that light up as quasars when feeding, IMB often lurk in sparse environments with little gas to form bright accretion disks. When they do snack on a passing star, the resulting tidal disruption flare might last mere months, a blink in astronomical terms, making them easy to miss. Another hurdle is their formation path. While stellar black holes come from dying stars and supermassive ones grow via mergers, IMB might require rare conditions like the direct collapse of massive star clusters in the early universe. Some could even be failed supermassive black holes, stunted by lack of food in their dwarf galaxy homes. Yet finding them is crucial. These missing links could explain how supermassive black holes achieved their gargantuan sizes so early in cosmic history. Did they grow from merging IMB like snowballs colliding to form an avalanche, or were they born large with IMB representing a separate evolutionary path? The answers might be hiding in upcoming gravitational wave detections. Collisions between IMB would produce low-frequency ripples that future observatories like LISA could catch. For now, these cosmic middleweights remain one of astronomy's most tantalizing puzzles, a reminder that even the universe's most dominant predators have secrets left to reveal. Dark matter has been the universe's most frustrating hide-and-seek champion, invisible, untouchable, yet making up 85% of all matter in the cosmos. For decades, scientists have searched for particles that could explain its gravitational grip on galaxies. But what if the answer isn't a particle at all? Enter primordial black holes, hypothetical relics from the universe's first seconds that might solve two mysteries at once. These aren't the black holes we know today, born from dying stars. They'd be cosmic leftovers, forged in the seething chaos of the Big Bang itself, when dense pockets of matter collapsed directly into black holes no larger than an atom yet as massive as a mountain. The idea isn't as far-fetched as it sounds. In the early universe, microscopic fluctuations in density could have created regions so compact that gravity overpowered everything else, squeezing matter into black holes before stars even had a chance to form. Ranging from the mass of a small asteroid to hundreds of suns, these ancient objects could be lurking everywhere in galactic halos between stars, even within our solar system. Their sheer numbers might account for the missing gravity we attribute to dark matter, all while leaving no trace beyond their subtle gravitational influence. But the theory faces fierce challenges. Microlensing surveys searches for the brief brightening of stars when invisible objects pass in front, have largely ruled out primordial black holes over a certain mass. If they were too common, we'd see more stars flicker than we actually do. The cosmic microwave background adds another constraint. Early black holes would have injected energy into the infant universe, leaving telltale scars on this afterglow of the Big Bang. So far, the data shows no such fingerprints, narrowing the window where these black holes could hide. Yet the hunt isn't over. Some versions of the theory propose black holes so small they evade current detection asteroid mass objects that behave more like a diffuse fog than discrete lenses. Others suggest they congregate in dense clusters, hiding in plain sight within galaxy cores. The upcoming Nancy Grace Roman Space Telescope could settle the debate, scanning millions of stars for the telltale flickers that might betray these shadowy suspects. If primordial black holes do explain dark matter, it would rewrite cosmic history. They wouldn't just be invisible anchors holding galaxies together. They'd be cosmic time capsules carrying secrets from the universe's very first moments. Every rotation curve of a galaxy, every gravitational lens bending light from distant quasars, might not be the work of exotic particles but of ancient black holes, silent and unseen, threading the cosmos since the dawn of time. The irony, the darkest entities in the universe could finally illuminate our deepest mystery. Sagittarius might seem like a quiet neighbor, but every now and then, our galaxy's supermassive black hole wakes up in a rage. While it spends most of its time in a dormant state, astronomers have caught this sleeping giant flaring sudden bursts of X-rays and infrared light that can brighten its surroundings by factors of hundreds in mere hours. These aren't random tantrums, they're cosmic feasts, moments when unlucky gas clouds or asteroids drift too close and get shredded by tidal forces, igniting the black hole's accretion disk like a match tossed into dry tinder. One of the most dramatic flares occurred in 2019 when an object named G2, a mysterious, dusty cloud, made a perilous close pass. Scientists initially predicted it would be torn apart, sparking a spectacular light show. Instead, G2 survived, but not unscathed. As it grazed Sagittarius A, the black hole's gravity stretched the cloud like taffy, stripping away layers of gas that spiraled into the accretion disk. The result, a flicker of activity, a hungry glow that betrayed the black hole's hidden appetite. Even when it doesn't fully consume its prey, Sagittarius A leaves its mark. Recent observations from the Event Horizon Telescope have peeled back another layer of this mystery. While we lack a direct image as sharp as M87's iconic shadow, the EHT's millimeter wave data reveals a flickering ring of light around our black hole, its brightness wobbling unpredictably. These aren't just random fluctuations, they're the fingerprints of magnetic storms and turbulent plasma swirling at the brink of the event horizon. Some flares even hint at hotspots, localized eruptions where magnetic fields snap and reconnect, launching bursts of energy akin to solar flares but with the power of 1,000 suns. What's fascinating is how these flares echo across the electromagnetic spectrum. Radio telescopes catch the aftermath, expanding bubbles of plasma pushed outward by the black hole's magnetic fury. Meanwhile, orbiting X-ray observatories like Chandra spot the initial violence. The moment gas heats to millions of degrees as it's compressed in the disk's deadly whirlpool. By stitching together these signals, astronomers are piecing together a timeline of destruction, from the first disruptive encounter to the final fade into silence. The flares also offer clues about Sagittarius A's past. Geological records on Earth show traces of radioactive isotopes that hint at a dramatic event around 300 years ago, a time when our black hole's X-ray output might have been 1,000,000 times brighter. Could Sagittarius A have been a quasar in the not-so-distant cosmic past? If so, its current calm is just a phase, a lull before the next meal stirs it awake. And with the EHT's resolution improving yearly, we're on the verge of witnessing these eruptions in unprecedented detail, watching as our galactic center proves that even the quietest monsters never truly sleep. Some stars don't just wander the galaxy, they flee it at breakneck speeds, racing into the cosmic void like bullets fired from a gravitational gun, the culprit behind these hypervelocity stars. The supermassive black hole at the Milky Way's heart, Sagittarius A, acting as a slingshot of unimaginable power. The star S5HV-S1 is one such escapee, hurled outward at a staggering 1,700 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 6 minutes. At that speed, it's not just leaving our galaxy, it's on a one-way trip into intergalactic space, never to return. The physics behind this stellar catapult is as elegant as it is violent. Picture a binary star system, two stars orbiting each other in a tight dance, drifting too close to the black hole's gravitational well. As the pair approaches, tidal forces rip them apart. One star gets captured, swirling into the black hole's orbit, while the other is flung outward with enough kinetic energy to overcome the Milky Way's gravity entirely. This Hill's mechanism, named after astronomer Jack Hills who first theorized it, turns black holes into cosmic pinball machines, flinging stars across the universe with precision. What makes S5 HVS1 so special isn't just its speed, but its origin story. Traced back along its trajectory, its path points directly to Sagittarius A, like a cosmic fingerprint linking it to the violence at our galaxy's core. Unlike supernova ejections, which can also accelerate stars, hypervelocity stars like this one bear pristine chemical signatures unchanged by explosive nucleosynthesis, offering astronomers a rare sample of the pristine material swirling near a black hole. These stellar outcasts are more than just celestial curiosities. They serve as probes, their trajectories mapping the hidden gravitational fields of the Milky Way. By tracking their paths, scientists can infer the distribution of dark matter, the invisible scaffold shaping our galaxy's structure. And because hypervelocity stars travel so far so quickly, they carry information about conditions near the black hole billions of years ago, preserved in their speed and composition like messages in a bottle. The universe is full of runaway stars, but none with the unmistakable pedigree of a black hole's handiwork. Each hypervelocity survivor is a testament to the raw power lurking at the Galactic Center, a place where gravity doesn't just bend the rules but rewrites them entirely. Black holes don't just consume, they might also remember. Hidden within their gravitational grip could be echoes of the universe's infancy, preserved like cosmic fossils in the fabric of spacetime itself. This idea clashes with the famous no-hair theorem, which suggests black holes are the universe's ultimate simplifiers defined only by their mass, spin, and charge, with all other details lost forever. But what if reality is messier? New research hints that black holes might hold onto subtle imprints of their past, like shadows of the material they've devoured over billions of years. Take the no-hair theorem's limitations. While it works perfectly for idealized black holes in a vacuum, real black holes live in chaotic environments. Matter falling in isn't smooth, it's lumpy, magnetized, and turbulent. These imperfections could leave faint gravitational hair, tiny distortions in the black hole's structure that encode information about its history. Imagine throwing a stone into a pond. The ripples fade, but the water never quite returns to its original state. Similarly, a black hole's event horizon might ripple with gravitational waves long after a star or gas cloud has been swallowed, carrying a faint record of what fell in. Some theories go even further. Quantum mechanics suggests information can't truly vanish, it might be scrambled and stored on the event horizon like a hologram. The black hole's surface could act as a cosmic hard drive, etching every ingested particle's quantum state into microscopic fluctuations. This isn't just abstract math. When black holes evaporate via Hawking radiation, that information might leak back out, encoded in the radiation's subtle patterns. It's as if black holes aren't just tombs, they're libraries, their walls inscribed with the stories of everything they've ever consumed. The implications are staggering. If proven, it means the oldest supermassive black holes could hold clues about the universe's first galaxies, the composition of primordial gas, even the conditions moments after the Big Bang. Their shadows might hide the fingerprints of long-vanished stars, the chemical makeup of ancient quasars, or traces of dark matter interactions we've yet to detect. Future gravitational wave observatories could hunt for these whispers, listening for the faint echoes of black holes ringing down after mergers, their vibrations revealing secrets about their formation. The universe's earliest black holes might be more than monsters. They could be time capsules holding answers to questions we haven't even thought to ask yet. And as we learn to decode their hidden language, we're not just studying black holes, we're reading the autobiography of the cosmos. The universe isn't just expanding, it's flowing, an invisible river of galaxies pulled toward something colossal hidden beyond the cosmic horizon. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging the Milky Way and thousands of other galaxies toward the Norma cluster at over 2 million kilometers per hour. But what's behind this mysterious tug? The answer might lie not just in visible matter, but in the hidden architecture of supermassive black holes and dark matter weaving the largest structures in existence. Picture the Great Attractor as the deepest part of a cosmic watershed where gravity's currents converge. At its heart sits the Norma cluster, a dense knot of galaxies packed with supermassive black holes, each weighing billions of suns. These monsters don't just anchor their own galaxies, their collective gravity, combined with vast halos of dark matter, creates a gravitational well so deep it bends the motion of everything within hundreds of millions of light years. Simulations suggest that black holes in such environments act like weights on a cosmic tapestry, their mass warping spacetime enough to steer entire galaxy superclusters. But there's a twist. The Great Attractor isn't the end of the journey. Beyond it lies an even larger structure, the Shapley supercluster, a staggering collection of galaxy clusters with a combined mass 10,000 times that of the Milky Way. Some researchers believe this distant behemoth might be the true source of the pull, its gravity funneled and amplified by the intervening black holes and dark matter scaffolding of the Norma cluster. It's like a chain of cosmic dominoes with supermassive black holes as the pivot points directing the flow. The real shock came when astronomers mapped the region in X-rays. Hidden behind thick curtains of dust in the Milky Way's disk, they found the Norma cluster's central black holes weren't just massive. They were surrounded by immense, glowing clouds of hot gas. These reservoirs of matter, heated to millions of degrees, trace the outlines of dark matter filaments connecting galaxies across the supercluster. The black hole's gravitational pull doesn't just affect nearby stars, it shapes these intergalactic highways, channeling galaxies along invisible routes like marbles rolling down a tilted sheet. What makes the Great Attractor truly enigmatic is its timing. Our local galactic neighborhood is rushing toward it now, but in the far future, dark energies accelerating expansion will likely tear us away, leaving the attractor as a relic of an earlier cosmic era. For now, though, it's a stunning reminder that black holes aren't just local terrors, they're the architects of the universe's largest motions, their gravity echoing across scales we're only beginning to comprehend. The Great Attractor isn't pulling us toward oblivion, but toward a deeper understanding of how the cosmos builds its grandest designs. Hollywood has a love affair with black holes, but it doesn't always stick to the science. Take Interstellar's Gargantua, a breathtaking visual masterpiece that gave us the most accurate black hole depiction ever put on screen, right up until it turned into a magical bookshelf. The film's portrayal got so much right: the gravitational lensing, the swirling accretion disk, even the time dilation near the event horizon. But then it veered into fantasy, suggesting you could survive a plunge into the singularity and somehow communicate across dimensions. In reality, crossing the event horizon isn't a gateway to cosmic enlightenment, it's a one-way ticket to being atomized. The most persistent myth, that black holes suck everything in like cosmic vacuum cleaners. Gravity works the same around a black hole as it does around any massive object, it's just stronger. If you replaced our sun with a black hole of equal mass, Earth's orbit wouldn't change. You only fall in if you stray too close, like wandering into the pull of a waterfall's current. The difference is, with a black hole, there's no paddling back. Then there's spaghettification, the gruesome fate Interstellar glossed over. When Matthew McConaughey's character descended toward Gargantua, he should have been stretched into a human noodle long before reaching the event horizon. Smaller black holes would tear you apart thousands of miles out, while supermassive ones might let you cross intact only to shred you inside where tidal forces twist space into knots. Even sound gets butchered. Space is silent, yet films like Event Horizon and the Black Hole crank up the dread with ominous rumbles. In truth, the only sound a black hole makes comes from pressure waves in surrounding gas, detectable as musical notes millions of times deeper than human hearing. NASA once translated those vibrations into audible tones, and the result wasn't a horror movie screech, it was an eerie, cosmic hum. Some tropes, though, are pure fiction. No, you won't emerge in another universe contact, and no, black holes aren't portals for time travel Star Trek. The closest thing to wormhole physics remains theoretical, requiring exotic matter we've never found. Even Doctor Who's TARDIS teasing time vortex is more fairy tale than relativity. Yet these myths persist because black holes feel supernatural. They warp light, freeze time, and erase matter, perfect fodder for storytellers. The irony, reality is stranger. A black hole's true power lies not in destruction, but in transformation. Every atom it swallows fuels jets that sculpt galaxies, and every ripple in spacetime carries secrets about the universe's birth. Hollywood's versions may thrill us, but the real thing, it's rewriting physics. The next decade promises to crack open the black hole playbook like never before, thanks to instruments so advanced they'd seem like science fiction a generation ago. Leading the charge is LISA, the Laser Interferometer Space Antenna, a gravitational wave detector so sensitive it could hear space-time ripple from collisions that happened when the universe was half its current age. Unlike ground-based observatories like LIGO, which catch high-frequency waves from stellar mass black holes, LISA-3 spacecraft will orbit in a perfect triangle 2.5 million kilometers apart, forming a detector vast enough to sense the low-frequency rumbles of merging supermassive black holes. Imagine listening to the universe's bassline, the slow, cosmic drumroll of million solar mass giants spiraling toward cataclysmic mergers. These events don't just warp space, they twist time itself, ringing spacetime like a bell in tones that could reveal hidden dimensions or flaws in Einstein's relativity. Then there's the 30-meter telescope, or TMT, poised to peer into galactic cores with resolution 10 times sharper than Hubble. Its segmented mirror, spanning nearly the length of a blue whale, will capture the faintest whispers of light bending around black holes' event horizons. While the Event Horizon Telescope gave us our first ghostly silhouette of M87's black hole, the TMT could map the magnetic fields threading these monsters' accretion disks in real time, watching how they launch jets at nearly light speed. It might even spot stars orbiting closer to Sagittarius than ever before, their tortured paths testing gravity's limits under conditions so extreme that Newton's laws crumble. But the real game changer, combining these tools, picture LISA sensing a supermassive black hole merger billions of light years away, while the TMT and its cousins, like the extremely large telescope, train their gaze on the aftermath, catching the relativistic fireworks as jets punch through galactic gas. This multi-messenger approach could solve enduring mysteries. Do merged black holes recoil, kicked sideways by gravitational waves like a rifle's backlash? Do their event horizons wobble like Gel-O before settling into a new, unified shape? Each observation would be a stress test for general relativity, probing whether black holes truly are as simple as the no-hair theorem claims. And lurking in the wings are wild cards like the Square Kilometre Array, a radio telescope network so vast it could detect the faint glow of primordial black holes evaporating from Hawking radiation. Or the Nancy Grace Roman Space Telescope, which might catch the flicker of intermediate mass black holes snacking on stray stars in globular clusters. We're not just building better tools, we're assembling a cosmic detective kit, each instrument specialized to uncover a different piece of the black hole puzzle. The era of static snapshots is ending. What's coming is a dynamic, multidimensional portrait of black holes in action, revealing not just how they look, but how they live. Could the most hostile environments in the universe, black holes, somehow cradle life? It sounds like pure science fiction, but nature has a habit of thriving where we least expect it. Right here on Earth, extremophiles flourish in boiling hydrothermal vents, radioactive reactor chambers, even the vacuum of space aboard the International Space Station. If life can cling to existence in these deadly niches, why not near a black hole? Consider the improbable oasis of an accretion disk. While the inner regions are sterilized by intense radiation and tidal forces, the outer edges might harbor a Goldilocks zone, a turbulent but energy-rich environment where microbial life could theoretically tap into the disk's heat and magnetic fields. Imagine organisms evolving to harvest energy from X-ray flares or photosynthesis-like processes fueled by the glow of superheated gas. These wouldn't be life as we know it, but something stranger, perhaps silicon-based or plasma embedded, with biology rewritten by the extreme physics of relativistic spacetime. Then there's the wilder possibility: civilizations inside a black hole. Russian cosmologist Vyacheslav Dokukiv once proposed that certain rotating black holes could contain stable orbits within their inner horizons, shielded from the crushing singularity. In this bizarre pocket of space-time, an advanced civilization might harness the black hole's energy, using frame-dragging effects like a cosmic water wheel. Their sky, a warped panorama of the entire external universe, condensed into a blinding ring of light circling the horizon. Of course, this stretches known physics to the breaking point. Any life inside would need to endure infinite tidal forces in some models, or navigate closed time-like curves where cause and effect loop back on themselves. And yet, black holes constantly defy expectations. Their jets funnel organic molecules like methanol across galaxies, seeding the building blocks of life far beyond their lethal cores. Their energy output could power Dyson spheres for unimaginably advanced civilizations, turning a destructive force into an engine of survival. Perhaps the most tantalizing clue comes from the Fermi paradox itself. If intelligent life is common, where is everyone? Maybe they're hiding in the last places we'd think to look, not around quiet stars, but near the universe's most violent power sources, tapping into energies we're only beginning to comprehend. Black holes might not just be tombs, they could be the ultimate cosmic cradles, hiding forms of life so alien we wouldn't recognize them until we learn to see the universe through gravity's darkest lens. What if every black hole is a cosmic womb, birthing an entirely new universe inside its crushing depths? This mind-bending idea isn't science fiction, it's a serious theory proposed by physicists like Lee Smolin, who suggest black holes might be the engines of a sprawling multiverse. Imagine our entire cosmos with its billions of galaxies as just one bubble in an infinite foam of universes, each spawned by a black hole in apparent reality. The math hints at something astonishing. When matter collapses into a singularity, the extreme conditions could trigger a rebound, a Big Bang in miniature, creating a newborn universe with physics subtly tweaked from its parent. Smolin's version of this idea, called cosmological natural selection, adds an evolutionary twist. Universes that produce more black holes better at cosmic reproduction would dominate the multiverse over time. It's survival of the fittest on a grand scale. Black holes act as universe factories, and the laws of physics in each offspring might shift slightly, favoring those that maximize black hole production. In this view, our universe's finely tuned constants, like the strength of gravity or the mass of electrons, aren't lucky accidents. They're the result of eons of cosmic trial and error, honed to optimize black hole creation. Not everyone's convinced. Critics point out there's no way to observe these child universes. They're forever hidden behind their parent black holes' event horizons. Without testable predictions, the theory skirts the edge of philosophy. Others argue that even if new universes form, there's no mechanism ensuring their physics would evolve toward black hole abundance. The randomness of quantum fluctuations might scramble any inherited order, leaving Smolens's selection process stranded in metaphor. Yet the idea persists because it solves puzzles. Why does our universe seem perfectly calibrated for black hole formation? Why do stars, galaxies, and even fundamental particles seem arranged to funnel matter toward these gravitational pits? If black holes are cosmic seeds, it would explain their eerie centrality in the grand scheme. Some string theorists even suggest that the information swallowed by black holes doesn't vanish. It's reworked into the fundamental parameters of a new universe, rewriting the rules of physics in the process. The most radical implication, our universe might itself be the offspring of a black hole in some higher dimensional reality. The Big Bang could have been the white hole eruption of a parent universe's collapsed star, making every galaxy, every planet, every atom the echo of another cosmos death. It's a humbling thought that the monsters we fear as destroyers might, in the grandest view, be the creators of everything. Even the mightiest black holes are not eternal, their reign will end. Not with a bang, but with a whisper stretched across timescales that dwarf the age of the universe itself. Picture the cosmos tens of trillions of years from now, long after the last stars have flickered out and galaxies have faded to darkness. Supermassive black holes, once the vibrant hearts of their domains, will face three possible fates, each more surreal than the last. First, the slow dance of mergers. As galaxies collide and combine over eons, their central black holes spiral together in gravitational embraces, locking into orbits that tighten over millennia. Eventually, they collide, releasing bursts of gravitational waves that briefly outshine the entire universe. The resulting single black hole grows larger, a cosmic titan feasting on the remnants of its predecessors. In this distant era, the universe may be dominated by a handful of monstrous black holes, each weighing hundreds of billions of solar masses, drifting through an ocean of expanding nothingness. But even these giants aren't invincible. Thanks to Hawking radiation, the faint quantum glow that slowly bleeds a black hole's mass, they too will decay. For a supermassive black hole, the process is agonizingly slow. One with the mass of our Milky Way Sagittarius would take 10 to the power of 87 years to evaporate, a number so vast it exceeds all the atoms in the observable universe. Yet as the eons pass, their evaporation accelerates. In their final moments, they vanish in a flash of gamma rays, their energy returning to the cosmos in a fleeting spark. Then there's the third path, the dark galaxies. When all stars have burned out and interstellar gas is exhausted, some supermassive black holes may linger in nearly empty halos of dark matter, their gravity the only glue holding remnants of their galaxies together. These ghostly structures, devoid of light but brimming with invisible mass, could be the last landmarks in an ever-expanding void, the ultimate irony. The same black holes that once devoured stars and shaped galaxies may become the last sentinels of a dead universe, slowly fading echoes of a time when the cosmos burned bright. Their endings reveal the universe's deepest truth. Nothing lasts forever, not even darkness itself. Black holes are the universe's ultimate paradox, objects so extreme they defy not just our intuition, but the very laws of physics as we know them. For all our equations and telescopes, there's a boundary we'll likely never cross, the singularity. That infinitesimal point at a black hole's core, where density becomes infinite and spacetime curvature breaks into pure chaos, is more than a mathematical oddity. It's a brick wall for human comprehension. Our theories shudder to a halt here, not because they're flawed, but because they were never built to describe a place where time and space cease to function. Consider this: Einstein's general relativity, our gold standard for gravity, paints black holes as geometric shapes, smooth, warped space. but quantum mechanics insists that information can't vanish, hinting that singularities must somehow preserve what falls in. These two pillars of modern physics, each proven correct in their domains, clash violently here. It's like trying to describe a symphony using only the rules of calculus. The tools just don't fit. The singularity isn't just unknown, it may be unknowable, a realm where concepts like before and after lose all meaning. This humbling limitation isn't failure, it's inspiration. Every time we hit these walls, science evolves. The struggle to reconcile black holes with quantum theory birthed string theory and holographic principles. The search for their hidden mechanisms led us to gravitational waves and spacetime ripples we now detect routinely. Even Hawking radiation, a whisper of quantum defiance against black hole darkness, emerged from confronting these very paradoxes. And yet, the more we learn, the stranger they become. Take the holographic principle, suggesting a black hole's interior is a projection of information encoded on its surface. Or loop quantum gravity's proposal that singularities might bounce, birthing new universes. These aren't idle speculations, they're revolutions in disguise, proof that black holes don't just guard their secrets, they rewrite the rules for uncovering them. Perhaps that's their greatest lesson. Some truths are too vast for any single framework. Just as a fish can't grasp the concept of fire, our brains, shaped by a world of 3 dimensions and linear time, may lack the hardware to process singularities. But in that gap between understanding and awe, curiosity thrives. Black holes aren't cosmic dead ends, they're luminous question marks, urging us to think bigger, dig deeper, and embrace the beauty of mysteries we may never fully solve. They remind us that science isn't about having all the answers, it's about having the courage to keep asking better questions. From the terrifying reality of spaghettification to the mind-bending holographic principle, these 30 secrets reveal black holes not as cosmic dead ends, but as the universe's most enigmatic architects. They shape galaxies, warp time, and might even birth entirely new realities. Who knew that a singularity could hold echoes of the Big Bang, or that hypervelocity stars could be catapulted across space by black hole slingshots? And let's not forget the great attractor, silently dragging galaxies toward some unseen cosmic nexus, or the possibility that dark matter itself could be made of primordial black holes left over from the dawn of time. Every discovery peels back another layer of mystery. Take Hawking radiation, proof that even black holes aren't eternal, or the bizarre quantum hint that information swallowed by these monsters might still linger, encoded in ways we're only beginning to grasp. Then there's TON 618, a black hole so massive it defies logic, and the missing middleweights lurking in the shadows, waiting to rewrite cosmic history. And who could ignore the Hollywood myths we've debunked? No, black holes don't suck like vacuum cleaners, and no, you wouldn't survive a plunge to send messages from the afterlife. Reality is already strange enough without the embellishments. Now it's your turn. Which secret left you rethinking the fabric of existence? Was it the way black holes regulate star formation like cosmic thermostats, or the chilling thought that they might be universes within universes? Drop your cosmic aha moment in the comments below. We could talk about these monsters for lifetimes and still only scratch the surface. And if your brain's still buzzing from this deep dive into spacetime's greatest enigmas, hit subscribe. The universe has plenty more mysteries to unravel, and we're just getting started.